Hello and welcome to T Academy. In today's lecture, we'll be analyzing a half-wave rectifier circuit with an inductive load. We have already seen half-wave rectifier with a resistive load in one of my previous lectures. You can click the link if you are interested in watching that. In today's lecture, we'll be seeing what happens when we add an inductance L in series with the load resistance R. So let's proceed with the analysis. So here I have my voltage source Vs and I am denoting the output voltage by Vd. So this is the voltage which appears across the inductance L and the resistance R. Now we already know from half-wave rectifier operation, which we learned in one of my previous videos, that when the input voltage Vs is less than 0, the diode is reverse biased and it behaves as an open circuit. So in this case, the output voltage Vd will be equal to 0. Now when the input voltage Vs becomes greater than 0, then we'll be assuming here an ideal diode, which means that the diode will behave like a short circuit and the output voltage Vd will become equal to Vs. Now let's say at time equals 0, the input voltage has become positive. Then for t greater than 0 up to a time period t1, there will be a current IR flowing through this circuit, and this current will be increasing. So within this time duration, IR will be increasing, and since the voltage across the resistor VR is given simply by R times IR, the voltage VR will also be increasing. But in this duration, the input voltage Vs will be greater than VR, and thus there will be a positive drop VL across the inductance L, since VL is given by Vs minus VR. So Vs is greater than VR, thus VL is positive, and the inductor is essentially storing energy in its magnetic field during this time duration from 0 to t1. Now at t1, the voltage across the resistor VR becomes equal to the input voltage Vs. So in this condition, the current IR flowing through the circuit will be maximum. For t greater than t1, the voltage VR will be greater than Vs. Therefore, the drop across the inductance VL will be negative. So here VL was positive, so this was greater than 0. For t greater than t1, VL becomes negative, and this essentially means that the inductor reverses its polarity and starts to supply the energy stored in its magnetic field back to the circuit. So the current flowing through the circuit IR will now continue to decrease. So it reached its maximum at t1. For t greater than t1, IR is decreasing. So IR continues to decrease till a time comes at t2 where the input voltage Vs becomes equal to 0. Now we saw from the half wave rectifier operation with a resistive load that as soon as Vs becomes equal to 0, the diode will be reverse biased and there will be no current. But in this case, the inductor still has to release its energy back to the system, and the current IR will not be equal to 0. It will continue to flow till the inductor has completely released its energy. And how do we know when the inductor has released its energy back to the system? This we will see from the plots that I will show, that in essence the volt second area during the charging phase should be equal to the volt second area during discharging. So once this condition arrives, the current will go to 0 and this circuit will go into reverse bias where the diode will have a negative voltage across it. So these are the phases through which this circuit goes, and it will become more clear now with plots of LTSpice because I simulated this simple circuit in LTSpice, and once we'll go over it, then you'll see all this interesting phenomena from the plots. So these are the plots of the input voltage, the output voltage Vd, the voltage across the resistor Vr, the current through the circuit IR, then this V, Vd, Vr is the inductor voltage, since if I subtract Vd from Vr, then I get the voltage across VL, and V, Vs, Vd is the diode voltage, which you can see has reverse bias during the negative cycle. So we are starting here at t equals to 0, and the input voltage is positive. The resistor voltage Vr is less than Vs, so Vs minus Vr is positive in this region, and thus the current, as I explained, IR, should be increasing. And this is indeed the case here from this red curve which you can see. So this trend continues till the point arrives at T1 where the voltage Vs is equal to Vr, and thus the current IR has a maximum here. Then for t greater than T1 in this region, Vr is greater than Vs, and thus the inductor voltage VL will be negative, which by the way you can see from this second pane. So VL becomes negative after t equals to T1, and this happens because this blue curve Vd, so Vs and Vd is the same, that's why they are overlapping. Vs is less than Vr, and thus the current through the circuit IR is also decreasing. But the interesting point arrives when we see at t equals to T2, when the input voltage has become equal to 0, the current, if I see from the red plot and the Y labels on the right hand side for the current, I see that there's still a current of 90 amperes flowing in the circuit even though the input voltage has become equal to 0. And this happens because the inductor still has some energy left that it has to release back into the circuit. And how can we find out the point where the current becomes equal to 0. So this point, which is T3, this will occur when the volt second area of the inductor voltage during the discharge period, let's call it area B, is equal to the charging period. So this positive part of the curve, let's call it A. So when these two areas under the curve become equal, then at that time the inductor has completely released its energy and diode goes into reverse biased operation, which we can confirm from this plot of the diode voltage. So this is the diode voltage, which should sustain the negative half cycle of the input voltage. So that's it for today's lecture. I hope the operation of a half wave rectifier circuit with an inductive load is clear to you. So in the next lecture we'll start with single phase rectifiers. So stay tuned to my channel and I hope to see you again.